All right, good morning, everyone. Let's go ahead and get started. Welcome to day 11 of Organometallics. Thanks for joining us on Friday today. So today we're going to keep moving forward into discussing historically and synthetically important catalytic reactions that integrate all of the elementary steps that we've covered in detail. Last class, we discussed hydrogenation, where the key principle is this sequence of oxidative addition to form a metal dihydride, migratory insertion, and then CH reductive elimination. And now we're going to examine catalytic cycles that are a little bit more complex, where there's an additional reaction component integrated. And these are carbonylation reactions. And so there are several different flavors of reactivity, some of which are mechanistically quite connected, some of which are a little bit disparate. The two main topics we're going to focus on today are, first, for roughly the first third of the class, the Santoacetic acid process, which is one of the most commercially important applications of homogeneous catalysis. And then for the latter two-thirds of the class, we'll talk about hydroformylation. There are some other reactions I'll just note. So I should say hydroformylation and other quite closely related reactions like hydrocarboxylation. I should note that there are other reactions that fall under the umbrella of catalytic carbonylations, such as the Pausen-Kahn reaction, which Professor Schmidt discussed in the cycloaddition class. And so not all of those would be covered today. Particularly for the Pausen-Kahn and related reactions, I'd reference her lecture on that topic. Okay, so let's go ahead and jump right in with the discussion of the Santoacetic acid process. So one of the themes that you'll see in today's class is now the involvement of CO as an actor ligand in catalysis. And so I think that there's also this sort of deeper connection, if you think about the previous class and today's class, which is that these are ways to productively utilize true chemical feedstocks, dihydrogen, which we covered last time, and then dihydrogen, and the most ubiquitous and arguably useful C1 feedstock, which is CO, in today's class. And so I think that these elementary processes really underlie a lot of modern society when you dig into it. Hopefully that will come through in today's lecture. And so, as I mentioned, the Santoacetic acid process developed at Monsanto is one of the largest applications and most successful applications of homogeneous catalysis. The use of acetic acid on a global scale is absolutely massive. You see here this figure of 17 billion pounds per year, and 80% of that is based on some type of methanol carbonylation technology. So that would include historically the Santoacetic acid process, though there are some newer processes that we'll just cover in passing today, but that follow similar principles. And the Santoacetic acid process and reactions within this family are quite well understood mechanistically. That's historically been important because it's allowed people to really go in and make hypothesis-driven perturbations to both the catalyst structure and the reaction conditions in order to improve reactivity outcomes. This reaction we'll see in the specific example, or the specific cycle that we'll cover today with rhodium, but essentially all group 9 and group 10 metals can be used in this chemistry. And the key is that they need to be used in combination with iodide anion, which is typically used as a co-catalyst. And we'll come back to the role of that in just a minute. But in terms of synthetic utility and utility on commodity chemical scale, I think this has to do with the fact that methanol is essentially one of the most important C1 feedstocks, and this allows for a nice selective one-carbon homologation. And so methanol can be made on massive scale from syngas, which is a mixture of H2 and CO, which in turn is typically generated from petrochemical feedstocks, but in the modern world can also be generated from biorenewables. So let's consider now the catalytic cycle for this reaction. So here's a general depiction of the reaction. Essentially, what's going to happen is, overall, is that you break a carbon-oxygen bond between the alcohol and the methyl group and insert this reagent, which in my lab we like to think of these types of reagents as conjunctive reagents, meaning that there's sort of two well-defined sites for bond formation. And so we can break this bond here and insert across this conjunctive reagent CO. And that reaction is catalyzed by various pre-catalysts, but I've drawn here what is commonly believed to be the active form of the catalyst. And relatively high pressure, relatively high temperature. But even under these relatively forcing conditions, the catalyst is still robust. I mean, one of the things that you can appreciate just at the outset is that acetic acid, though valuable, is not an expensive reagent. You get it by the drum. And so the product in this case is very cheap. And so because you're using a relatively expensive catalyst in a rhodium-based catalyst, it needs to just be incredibly robust. A massive number of turnovers to be commercially viable, and that is indeed the case. Okay, so let's walk through the catalytic cycle, and this will be used then as a springboard for problem of the day number 1. So I haven't drawn the catalyst activation step, but let's assume here that's implied. So you have some rhodium precatalyst. What you're going to form is now a rhodium 1 dicarbonyl or bis iodide complex. And the coordination of two iodide groups here is critical because this makes the catalyst anionic and quite electron rich. And so what can then happen is a oxidative addition event with methyl iodide to generate now a rhodium 3 complex. Migratory insertion of the methyl group into CO to make an acyl rhodium. And then now what can happen is I reductive elimination. You could think of this happening inner sphere, or you could think of this happening outer sphere. We'll come back to this point to generate acyl iodide, and then this, in the presence of water, is hydrolyzed to acetic acid. Concomitantly, the methanol that you're using as a starting material is interacting in the second catalytic cycle with HI or some I minus source to be converted in situ into methyl iodide. And so a very elegant cycle to sort of simultaneously activate what you might think of as being a recalcitrant group in the CO bond of methanol, and then using it productively in the cycle. So problem of the day number 1, if you'll turn to that, asks you to consider how this key oxidative addition step might be happening. And so if you think back to our lecture on oxidative addition, you'll remember that there are several established mechanisms for oxidative addition in general, and then some that are better suited than others when you're thinking about an alkyl halide coupling partner. So Han Sol, what are some possibilities here for oxidative addition? No Han Sol? Kai, how about you?
Maybe it's conservative or SN2 or ionic process.
Oh, Han Sol, you just missed out. I'm being called on. Okay. That means you're first in line for the next part. Okay, concerted, and then SN2, And what was the third one? Ionic. Okay, how's that different than SN2?
Maybe the OH will not happen in this case.
Okay, and then any other general possibility that we covered?
Single electron transfer.
SCT. Okay, so let's call this radical. Okay. Okay, and if we wanted to go, of course, this mechanism is not quite well understood, but let's say we're 40 years earlier and we're trying to get a handle on what's going on here. What experiments might we do to shed some light on this? Zhishi, what do you think?
One thing we should do is to test the solid effect. If we use the reverse measure for the Rhodia problems, that means they probably go through the next stage.
Okay. What else? Jess? Okay. So let's use, so which ones are we trying to disambiguate here? Radical SN2 and potentially, if you can establish whether it's invertive or attentive, potentially these two pathways as well. So what kind of probe do you want to design here? You're thinking about a Norbornal substrate, okay. And so you can do, we use this as an example of probing radical versus SM2, or alternatively, I think you were kind of alluding to this too, you could do something like this. You have 1D, 1H, and some R here. Now, one of the things I would say I would urge some caution in, and a reviewer might flag you if you did this kind of experiment, is that when you make such a change of the electrophilic coupling partner, you might very well change the mechanism. And so if you want to study the Santoacetic acid process itself, then moving to other electrophiles might get you just different insight about a totally different reaction. Okay, but yes, I like that general idea. Any other ideas from the audience? Anyone can jump in. Sarah raised her hand first, Vincent. She beat you to the punch.
Can you see if they're added trans?
Yes, great idea. So how would you do that, though, when you have so many iodides? Okay, so you want to do some labeled version. Yeah, okay, like that. So let's label this, and then let's see where it goes. You basically have two inequivalent positions, either the axial, or either the equatorial or the axial. And so what would you expect if it's, say, SN2, where's it going to go? Yeah, if it's SN2, the label will go here. And if it's concerted, the label will go here. Okay? Okay, any other thoughts? Dichlororhodium. Okay, and what might you expect to happen there?
Just looking for the same thing, so rather than using...
Sure. Okay, great. You do this experiment, but use the dichlorodibroma. I can tell you, empirically, it's known that those types of catalysts or pre-catalysts are much less reactive. So that would be a complicating factor. And did you have an idea, Vincent?
I don't know if you'd be able to see this, but could you look at the COs, different CO stretches, and maybe deduce from that how rhodium's behaving?
CO stretching. I think the problem will be where, under the catalytic conditions, what's the resting state?
I see.
And if the resting state is before the step that you want to interrogate, then you will be potentially have some issues with that. Any other final? Yeah, go ahead.
So when you label the iodide, how do you distinguish it?
Then you would need to use some NMR technique, I think.
So it's iodide
Is there iodide NMR? I guess that you can find I guess that you can use a labeled form of iodide that will be NMR active, or at least it allows you to observe a coupling constant to something else, the methyl group. So, a lot of ideas. Okay, let's just do. I saw Max, and then let's do Tucker.
Only tensor benzoate.
Okay, radical inhibitor. Good. Tucker.
Did you see an inverse rate dependence on iodide concentration?
You, yes, could if that is indeed their rate determining step. So let's look at iodide concentration. And then another one, I'll just throw it up there, that might allow you to, I think would have probably a pretty dramatic effect in allowing you to disambiguate between radical and SN2 is remember that SN2, you have this effect where tazol is more reactive than iodide, and then in radical, you have this effect where iodide is much more reactive than tazol. And so that would be a way where you're still using a C1 electrophile, but you're changing the leaving group. And I think in general, in terms of mechanistic studies, this effect is probably underutilized in the literature. I think there's a lot you can learn from that. Okay, very good. And so and indeed, many of these types of experiments have been done over the years. And just to summarize, what's known, it is indeed believed to go through an SN2 pathway. So let me draw out how that looks, just so everyone's on the same page. So you have a filled orbital, d orbital on rhodium. And then, okay, I thought I would leave enough room for one more set of schemes, so I'm going to put it down here, even though it kind of belongs here. And then the other point I made was about how is this acyl iodide reductive elimination happening. And so if you were not to consume the acyl iodide that you generate through hydrolysis, then it would also react via SN2. And so now this is just like your standard organic carbonyl chemistry. So one-two addition in, and then loss of the better leaving group. And so the key point here is that I think it gives you some insight into how this reductive elimination step might take place by the principle of microscopic reversibility. And so reading left to right, we're considering an oxidative addition of the acyl iodide into rhodium. But if you read right to left, it would show you how the oxidative or how the reductive elimination could take place via an outer sphere pathway. Okay, a few more points of commentary on the Santoacetic acid process, and then we'll move forward to hydroformylation. So one of the side reactions from this electron-rich rhodium-1 anionic species is that it can actually directly react with the HI catalyst, and so I've drawn a couple elementary steps, two arrows here indicating that a few elementary steps then need to happen. But suffice to say, the byproducts from that event can be rhodium-3 species. So rhodium triiodide, which is less soluble in the reaction medium, as well as this rhodium tetraiodide CO2 or this carbon monoxide complex. And so a strategy that has been developed thinking about mechanistically what's going on here, and then through some empirical tuning, is that this process can be circumvented by adding some water, a controlled amount of water to this system. And what that does is that it allows you to consume rhodium-3 by this process called the water-gas shift reaction, and it also helps to solubilize. Didn't write that here. And so as technology, as the mechanistic understanding has advanced and technology in turn has advanced, there have been new generations of this type of methanol carbonylation technology. One is called the Tennessee Eastman acetic acid process, another is called the Cativa process that uses an iridium catalyst. And in the interest of time, I won't go into detail, but I would certainly encourage you to consult the Hartwig textbook for more information about those processes. But mechanistically, they're quite closely linked to this, so I think that it would just be more examples of building on this theme. Okay, so now let's move forward to a discussion of hydroformylation, which brings us to our chemist of the day. Does anyone want to take a stab? All right, this is the father of the OXO process, or also known as hydroformylation, Otto Roland. I guess probably the German spelling is like this. Maybe Leah can correct me if I'm wrong. And he was born in Mulheim and did his training, and this is actually a key point, with Fischer and Troche. And then known for hydroformylation. And one of the key points about his training background, so some of you will recognize the names Fischer and Tropsch from the Fischer-Tropsch process, which describes a collection of reactions that convert syngas to liquid hydrocarbons. And so not only did he train essentially developing that technology, but he was also in sort of this golden era of feedstock conversion catalysis that was going on in the Mulheim area. So this institute, Kaiser Wilhelm Institute of Coal Research, you'll probably recognize by its modern name, which is the Max Planck Institute for Kohlenforschung, where Carl Ziegler worked on polyethylene polymerization, and there's been many other breakthroughs, including the development of nickel cod. So he came through that training environment and then joined, I have it somewhere, I think, Ruhr-Chemie, where he was tasked with developing the Fischer-Tropsch process further for their own purposes, and actually serendipitously discovered this process that their legal team dubbed the OXO process, and then was later renamed by Atkins hydroformylation, which is what we typically refer to it by today. And so one of the things that's interesting, I would encourage people to read this Angewandte review, which is essentially a biography of Otto Roland's life. And one of the things that's quite interesting is that it actually includes essentially his written evaluations after his bachelor study and after his PhD study from his advisors. Like, he's a knowledgeable chemist, he works hard, his weaknesses are this, that, and the other. And so it just goes to show, if one day you become famous, be careful what Scripps has on file about you. Presumably you need some permission for release of that info. But anyway, so that's a fun read. Specifically, his key... So the Fischer-Tropsch process is very important, but we won't cover it in detail because it's mechanistically quite complex and because it's heterogeneous reactions, meaning that it's in general harder to interrogate mechanistically. But Roland's first discovery of this sort of first-generation system was with Cobalt carbonyl, and so throughout the next couple sections, you're going to see a lot of CO catalyst with CO ligand, and so hopefully that's clear. If it's not, then please ask for clarification. And then there's been further development of this, both with improved CO catalysts and more recently with rhodium-based catalysts. So synthetically, the reaction accomplishes the formal addition of formaldehyde across an alkene. I think that's probably obvious. And then it also, in terms of feedstock conversion chemistry, it accomplishes this one carbon unit homologation from a CN alkene to a CN+1 aldehyde, and that is a value-added process because these CN1 aldehydes are quite useful. And so, in general, these types of reactions, there are some side reactions that you might be able to anticipate based on what we've covered so far in class, so I'll just ask for volunteers if anyone wants to shout out some potential side reactions based on the chemistry involved and what we discussed last class period. Hydrogenation, okay. Tucker.
Isomerization.
Isomerization, okay. others? Polymerization. Okay. Actually, I think it's not a huge problem, but it could potentially be. Yeah.
Reduction of aldehyde.
Yeah, and then aldehyde reduction. Okay. Very good. Okay, so thermodynamically, it also deserves, I guess, brief commentary. So this reaction is, sorry, I lost my negative signs. It would be confusing if this was an endergonic reaction. So the reaction is exergonic, but not as much so as hydrogenation. So that's all I'm going to say about that. In terms of the general catalytic cycle, and then, so here's the general version, and then we'll see two more specific cases to really drive this point home. This is sort of the situation. Remember, at last class period, we covered the situation of metal monohydride carbonyl reactivity. And so this is the case here. And in that system, we studied from, or we discussed from Wilkinson. Remember that those are not the right reaction conditions for hydroformylation. That catalyst is a hydroformylation catalyst if you give it enough H2 and CO. So here's a general depiction. You have some open coordination site on your catalytically active species. You can coordinate an alkene. The next step is should look familiar: 1,2 migratory insertion, aka hydrometallation, to make an alkyl metal species. This open coordination site is then often going to be capped by CO. From there, you'll have CO migratory insertion to make an acyl metal. And most typically, all of these steps are reversible. It depends a little bit on the specific system in question. And then, in general, the irreversible step is, I've drawn it as a single step, but the proper way to think about this would be oxidative addition of H2 to make a dihydride, and then CH reductive elimination. And probably one of the contributing factors for why this step is a slow step is that now you have an acyl metal. You'd expect that to be more electron poor, and you're asking it to do an oxidative addition step that's going to be promoted by an electron-rich metal. Okay, so some other facts about hydroformylation. It's just used on an incredibly large scale. The figure that I found was that net is millions of tons, and if you just calculate that on a per person basis, it's 2 pounds of linear aldehyde per person on Earth per year. And I think that just goes to show, of course, none of us are using, unless you're using it like in total synthesis, you're not using 2 pounds of neat linear aldehyde, but because it's converted to so many different products, that's sort of where there's a lot of hidden utility there. So primary aldehydes historically are viewed as being more valuable than the corresponding branched aldehydes, which is convenient because, as you'll see, actually there's a tendency of these systems to funnel towards production of the linear aldehydes. And then one of the points that I think Tanner mentioned is that both cobalt and rhodium are known to be alkene isomerization catalysts, and so that manifests itself in the fact that these reactions can be regioconvergent, meaning that you can get the same product outcome whether you start from a terminal or internal alkene, and the explanation for that is depicted here, where with your metal hydride catalyst in solution, you're getting rapid alkene isomerization, and then the downstream steps are what ends up being selectivity determining. And so specifically in the situation I've drawn here, essentially everything and then isomerization, which was not drawn in the cycle, would be reversible, and the selectivity determining step will eventually be this either the H2 oxidative addition or CH reductive elimination step. And so this turns out to be useful because it allows you to take, and I think you see this now in in the modern literature with people doing similar types of approaches with nickel hydride chemistry, for example, where you can take a regiochemical mixture of starting materials and funnel into a single product. And this is known for a long time in the context of hydroformylation. Okay, so one of the big applications of hydroformylation chemistry is in production of materials, a variety of different materials, including detergents, plasticizers, etc. One plasticizer of broad importance is the one I've shown here, DEHP. So let's turn to problem of the day number 2, which asks you to provide a synthesis, or at the very least some disconnections, of DEHP from true feedstocks. And so, in case it's not obvious, a hint would be that it would be good to maybe use at least one hydroformylation step in your synthesis of this molecule. So why don't we take a minute, because even though it's a simple molecule, there are different ways to think about this, and then discuss with your neighbor, and then we can reconvene. All right, let's start getting some ideas for this one on the board. Anyone want to volunteer? What's that? Hans Holt, you want to volunteer? Okay, so let's break this first. Okay, phthalic acid. That is pretty cheap. And do you know how to make this? From Aldrich? Okay. I haven't seen this on retrosynthesis yet. It's really. Any ideas? We'll put this open to everybody and then go back to Hansel. What's that? Yeah. Wow. Great. Kai, you should get a whole bag of Starburst. Okay. So there are basically two ways. One is is naphthalene. That's right, E2O5 catalyst. So it's a sequence of oxidations. So you're oxidizing this bond multiple times and eventually cleaving it. And then the other way is to make it from xylene using similar oxidation chemistry. Very good. Okay. So yeah, even chemicals as simple as this, Aldrich has to get from somewhere. Okay, and then what about Hansel, the alcohol fragment? So this gets us to. Let me make sure I can draw this right. What do you think?
The alcohol has 8 carbons. I think we can do that. The condensation of aldehyde with 4 carbons.
Okay, like that.
That can be generated from hydroformylation of cocaine.
Okay. And maybe just so everyone's on the same page, I'll draw an intermediate here. So from this aldehyde, then I think, if I understood you correctly, Hansel, then you're going to want to do a aldol. 1, 2, 3, 4. And then a global reduction. Is that right? Good. Any questions or any other approaches? Yeah, I liked, Hansel, your analysis of the alcohol. Just keep it very simple. Okay, it's a C. You know you have to just chop off carbons. It's C8. Let's break it to 2 C4 pieces, and then let's break the 2 C4 pieces into 2 C3 pieces that we can do hydroformylation on, and then find a way to put it together. That works for feedstock conversion chemistry. It works less well for natural products synthesis.
Can you do starting with benzoic acid and do CH activation?
I think so that's interesting. So there are. Benzoic acid is also cheap. This is going to be made from toluene. And then the idea is that you want to have some, you want to have CO and then an alcohol.
Yeah.
And I think this is an interesting way to think about it. And probably you already know what I'm going to say next, which is that the catalytic efficiency of all modern methods to do this.
I wasn't suggesting it as a reasonable
10
industrial process.
Maybe 20 orders of magnitude below what's needed. But I think it shows the power of those kinds of disconnections and the opportunity for development. So yeah, it's like a different way to think about. Get out of that way. Oh, sorry. This way. Very good. Okay. So now we're going to move over to this part of the blackboard and talk about rhodium-based methods. So we covered Wilkinson's contributions to this area of development or area of research last time. And on the industrial side, the key contributors were research groups from Solance and Union Carbide in the 1970s. And these are sometimes, rhodium work in general are sometimes referred to as the second generation or low pressure hydroformylation methods. And so some of the advantages, I mean, it's an interesting example. I think you see cases in the literature where people will make a case for replacing a precious metal with an abundant metal. And here, on the biggest possible scale you could imagine, actually the development happened in the exact opposite direction, because it's just all about cost at the end of the day. And the advantages, of course, the disadvantage of rhodium is cost, but the advantages were numerous enough that they outweighed the disadvantages, so they were allowed, they could now use low pressure. The side reactions that we discussed earlier with cobalt were minimized. And also, I think you'll see that as we go through, is that with some of the best ligands for rhodium, you can get really high selectivity. So I guess I didn't go through some of this cobalt stuff. Okay, so now I'm going out of order. Yeah, okay. I got so excited about this problem of the day. Okay, so let me take one step back and provide a little more context. So, okay, cobalt. So cobalt-based systems came first, and then the rhodium systems. I'm getting a little bit ahead of myself. And so, as you saw, the first discovery by Otto Roland was with like the most simple cobalt catalyst you can imagine, and the mechanism of that was studied extensively. I think that the model that's still accepted to this day was developed by Heck and Breslow. This is not Ronald Breslow. This is a different Breslow, David Breslow. The selectivity, as we mentioned, is not is sort of controlled relatively by elementary steps relatively late in the catalytic cycle, and it's normally 3 to 4 to 1 linear to branched. This point becomes important when you start to compare the commercial viability to the rhodium-based systems. So Slough and Milano discovered the benefit of phosphine-based ligands. Their first discovery was with tributylphosphine, but of course there are other phosphines that can do the job here. And this really pushes the selectivity higher, and it allows for the use of lower CO pressure as well as higher temperature. So one explanation for that is that when you have a phosphine ligand, now your electron, so you're replacing basically one of your CO ligands with a phosphine. The electron at the metal center is now more electron rich, and it can participate in much enhanced back bonding with the CO. So remaining CO interactions become significantly stronger, and the catalyst overall becomes more stable. Okay, so here's the catalytic cycle, and I think when I realized when I was over here, I was thinking about like the catalytic cycle is kind of the same as with cobalt, and I realized I didn't talk about cobalt. Okay, so here's how things are believed to take place. So this can be thought of as like a bimetallic oxidative addition to make axial or apical cobalt hydride. Now, at this point, we need to lose one equivalent of CO to create a vacant coordination site. The alkene can coordinate. Now you have hydrometallation or migratory insertion, and the metal here has two choices. You can either insert with Markovnikov or anti-Markovnikov selectivity to give the branched or linear product respectively. And so in general, anti-Markovnikov selectivity is favored, but you do get appreciable amounts of this as well. Remember, all of these steps are drawn as being reversible. So now the open coordination site that was created upon migratory insertion can coordinate another CO, migratory insertion to make an acyl metal, and then a sequence of oxidative addition to make a cobalt dihydride, and finally acyl hydrogen reductive elimination to regenerate the active catalyst. And then there's an off-cycle process that can happen here. Remember, you do have a vacant coordination site, and you have CO in solution. So another equivalent of CO can coordinate. And of course, there's really no productive chemistry that can take place here. And so you can imagine at this juncture, every step on the cycle is drawn as reversible up until here, which is drawn as irreversible, and then you have some catalytically relevant intermediate, a way to partition it off cycle, and then a slow step here. So you can maybe think for yourself what you might expect the rate law in such a process to look like. Okay, now I think I've said what I want to say about cobalt, so let's actually move to a discussion of rhodium. And so I sort of discussed a little bit of the history of the development of rhodium-based hydroformylation catalysts and the advantages. Mechanistically, we're going to find that the situation is quite similar. The main difference is that now you typically have phosphine ligands. And so at each intermediate where we have nicely drawn symmetrical structures that have two COs, now you have twice the number of possibilities because you have one phosphine bound, at least one phosphine bound to the metal. And so let's draw out that cycle. Or rather, I won't draw the whole cycle, but I'll just sort of draw out the key intermediates, and then I think based on the cobalt cycle, you'll be able to understand what's going on. So let's consider like the most simple possible rhodium-based system. This is just triphenylphosphine as the ligand. And so this you can actually just observe experimentally, this equilibrium. And Brown has done this and found that it exists as an 85 to 15 ratio. And so now from here, when you coordinate CO, you can get two possible, when you lose CO, then you can have two possible geometric isomers. Similarly, when you then coordinate an alkene, same story. And then from here, each of these two isomers can undergo migratory insertion to get linear or branch. So then you're going to have 4 possible intermediates. And so I think hopefully the picture is clear here. It's the same chemistry you've already seen. It's just more things that need to be considered. These are all potentially in equilibrium. Now, depending on the individual system in question, which of these steps isn't actually reversible, and what can interconvert is going to be different, but just out of simplicity, we'll draw it this way. Okay. So some general reactivity trends. Nothing that's really going to surprise you here. So maybe this is so obvious you don't even need to write it down, but essentially more hindered alkenes react more slowly within the terminal series. So and that the steric properties of the substrate also can have a profound impact on selectivity. And the trend here, I think, is fairly obvious and intuitive. If you have steric bulk proximal, then you favor the formation of the linear product because the putative intermediate that you would need to make for hydrometallation in this direction places a rhodium directly adjacent to a fully substituted carbon center, which is sterically disfavored. Okay, so this brings us to problem of the day number 3, which I'll introduce with a little bit more background information. So some of the first generation systems here with rhodium were developed with simple monodentate phosphine ligands, and then it was found that the use of bidentate ligands can have a profound impact on the final selectivity outcomes, and one of your handouts actually summarizes some of the ligands that have been used in hydroformylation over the years. And so one of the ligands that has been found to be especially effective is the one that's shown in problem number 3, this EIS BI ligand, BISB ligand, that gives very high ratios of linear to branched. And so the question will ask you to explain, basically propose a model or propose what you think the origin of this phenomenon might be, and then also propose one or more experiments that might test the logic of this model. So let's just get an open discussion going on this. So, Dongman, what do you think? Oh, Dongman is not here today. Shuang, what do you think?
Is it because of steroids? Oh, so they bridged phospholipid, kind of blocked the phospholipid in the cis meta.
Okay.
So, if you have branched product, you will have steroids interaction with the bulky part.
Okay. You're definitely on the right track here. I think intuitively, you're basically, if I understand your reasoning, you're thinking a more bulky catalyst, in principle, should favor the linear product, because at some point you're going to make the branch product, you need to make a secondary alkyl metal, and the more bulky the metal, the less favored that is going to be. And remember that most, let's assume every step is irreversible until the final dihydrogen oxidative addition or steric elimination, then yes, I think that makes sense. And then the question is this ligand actually sterically bulkier, inherently sterically bulkier than, say, triphenylphosphine?
No.
And you'd say maybe, like, if you just consider the phosphine, a single phosphine in isolation, maybe you'd say no. Basically, it's like triphenylphosphine, but one of the phosphines is replaced with a methyl. So that you could reason is actually smaller. So what is a feature about this ligand that is very different than other ligands in ligands in general? Tanner is sitting on the edge of his seat.
Oh, no, I'm trying to get Zhang to...
Okay, Zhang is
Wait,
volunteered by Tanner. Okay, what do you think?
Well, I heard through the grapevine that this ligand is trans ligand.
How many grapes are on the vine? Two.
Just a couple.
That's it. Okay. So you've heard through the grapevine that it's a trans-spanning ligand. What does that mean?
Like the two phosphines are trans to each other
Okay.
because of the Y angle.
Oh, okay. I love it. That term is a key. Bite angle. And so this builds on Shuang's proposal. So the BISB is known to be a very wide bite angle ligand. We discussed bite angle before in class. So this is essentially just to refresh everyone's memory, bite angle is the angle here that a bidentate phosphine ligand will coordinate. And it's known that this BISB ligand has a wide bite angle. There are two ways to calculate bite angle. One is so-called natural. And so remember, the natural bite angle refers to considering the ligand in complex state with the metal, but not considering the effect of the metal's electronic, the geometric nature of the d orbitals involved in bonding. And So Bisbee has a natural bite angle of 112, and in the crystal structure you can see it has a bite angle of 124.
How does that compare to triphenylphosphates? It's trigonal planar, or if this is
Triphenylphosphine doesn't have a bite angle because it's monodifferent.
I know, but you would have like two phosphines coordinated at rhodium in that angle. Or I don't know.
Right, then it depends on which. So in a trigonal bipyramidal structure, then it depends which two sites you're talking about. If one is axial and one is equatorial, then it will be 90.
Oh,
Both
okay.
are equatorial, then it would be.
In this case, I'm just being equatorial.
Okay, so let's consider what Vincent just said. So the reason I make this, I went into this distinction between natural and measured bite angle is that it's been found in this area of research that the computed natural bite angle actually is a really strong predictor of linear to branched selectivity across the series of biphosphine ligands that have been examined. So now let's consider a wide bite angle ligand versus a narrow one, narrow bite angle bidentate ligand. So this is here is at the. I think this it's easier to see what's going on here if you consider the first intermediate drawn. Some of the others you have to use your imagination a little bit more. But this is the effect that Vincent was alluding to. The bite angle ultimately can dictate which of the two possible. Remember, we said with phosphines there's a bunch of different coordination geometrical isomers that can be accessed. And the bite angle here is going to help dictate which one is favored. And that, in turn, is going to affect the steric environment around the metal and the key selectivity determining step.
For these type of systems, the bidentate nature of the phosphine, does this also help with keeping the number of coordinated phosphines uniform? Versus if you have PPH3, you could have 1, 2, or 3
Yes.
coordinated, and this sort of makes sure that you only have 2
Yes, that's another
at once.
important consideration. And then we won't go in. So historically, as I said, the linear products have actually been viewed as being more valuable. But where the branch products, I think, start to get more interesting is if they can be made enantioselectively. And so there's many different ligand structures that have been explored over the years. These are summarized in the handout. Some of the best structures that have been uncovered are these phosphite-type ligands, often bidentate. In academia, one of the key early contributors was Van Leeuwen. And then in industry, Babin, Whitaker. So some of their ligand structures are on the handout. And these two are at Union Carbide. Okay, so before moving on from hydroformylation, let's consider problem of the day number 4. This is an intramolecular example. So for a little more background information, we've said a few times in class that that formation of the aldehyde is often reversible, but this does depend on the conditions that are being employed. So it is not always innocent in reaction solution. So that's going to be the key to getting started in this process. And then the crux of the problem, of course, first is to just make sure that you understand the arrow pushing to get the product, but then to rationalize this empirical outcome that when the reaction is around the presence of ethylene, that there's higher product, not only higher product yield, but higher higher conversion. But those go hand in hand. So higher conversion and higher product yield, something like that. So what's going on? Think about that and discuss with your neighbor. let's take a look at this. Saul, do you want to get us started on this one?
Sure. So I think the mechanism is rhodium-1 coordinates to the olefin and also in the sigma sense to the aldehyde.
Okay, what will the coordination environment of rhodium-1 be? What other ligands are you thinking?
Probably planar. So
Okay. So is this, you said sigma sense the aldehyde, is this what you had in mind?
I was saying, like, make a sigma free complex with the CH bond.
Okay, got it.
Prepare to do the observation.
Okay, just get right down to business. Okay, and then, so let's say, you said it's rhodium-1, so let's say 1 phosphine and 1 chloride. And now,
Do an oxidative
oxidative addition. Been pretty okay at drawing metallocycles over the years. Okay. And then what do we?
1, 2 migratory insertion.
1, 2. Okay. So we're gonna have.
You're going to get a sigma.
Okay.
You should have lost your hydride. Right, the hydride, so it's microscopic.
Thank you. Just for clarity. Okay. Okay. And what are you thinking in terms of ethylene effect?
So, the two things that I can think of are one that in the rhodium hydride complex, you can lose a hydride and have ligand exchange.
From this complex that you could lose a hydride?
That should. Oh, I guess not. 'Cause it's a ligand instead. The answer is I'm not sure.
Okay.
Um,
Any proposals? Dan?
So, if you draw the first step as CH oxidative addition, it's probably not very favorable. But if you have a pre-coordinated, hydride accepting ligand, such as ethylene, already coordinated, you can sort of trap the rhodium acyl species. And so when you do your oxidative addition, it won't quickly funnel back to starting material, but instead insert into ethylene. And this 1,2 insertion opens a coordination site, which can quickly be filled intramolecularly by the pentant alkene on the aldehyde. And then,
I think if I understand what you're saying,
yeah,
correct me if I'm not
no,
on the right
you're
track
drawing
here.
it right so far. Perfect.
And so your point is,
And then now this can
from here,
You can quickly coordinate the pendant alkene.
coordinate the pendant alkene, and then what? Oh, and then okay. So you coordinate this, and then you're going to undergo beta hydride
Yeah.
elimination to regenerate,
Sure. Yeah. Exactly. It's
and then you'll end up intercepting this again, right?
yeah, but it's a way to
this is a stable reservoir.
yeah to quickly prevent.
Okay, that's a reasonable proposal. Any other ideas?
Could be like from sols intermediate 2, you need to have the olefin and the hydride to be on the same side of the rhodium. It seems like it might either just oxidative addition CH be on the opposite phase, so you need something to displace the tethered olefin, let it do like a super rotation to the olefin on the same side as the hydride.
Okay. I know what you mean. Basically, just you're saying that this coordination is going to be dynamic, so having some ligands in solution can help you stabilize when you get to the cortically unsaturated intermediate that you need to isomerize. So what could this? Maybe let's think about this a different way. Is there anything that this could potentially decompose into? Let me redraw this without the alkene bound. It's actually essentially similar to this. I'm just going to draw this as an open coordination site. So what can happen here?
Splits off CO.
Yeah. So when you have an acyl metal and an open coordination site, we discussed previously how CO migratory insertion is often reversible, and so that can indeed happen here. Hopefully, if I'm misremembering this, Joe will give me some signal. Okay, good. And so the idea now is that it is, I think, related to the point that Tanner made, but that in general, having open coordination sites in the system is problematic because it can allow you to get here, and then from here, you reductively eliminate and get to a dead end. And so by having ethylene, you erase this because the structure is already gone. When you have ethylene in solution, it allows you to sit here more of the time and be in this productive exchange rather than going down that pathway. That's at least a proposal. There might be other things, other ways that one can think about it. And Tanner might be looking at this saying, yeah, but from here, you're really going to undergo migratory insertion, and then it's just my explanation. And that's a fair point.
So why is ethylene better than just adding more trifenophosphine?
That's a really good question. I don't know. I'd have to go back and look if they did a systematic study of triphenylphosphine loading. I think when you're under ethylene pressure, you can get to really high metal to ligand loading that would be kind of like preposterous to do with triphenylphosphine, if that makes sense. You can be 100-fold, 1,000-fold excess.
I think also the triphenylphosphine is apparently better at deformylation. Right?
triphenylphosphine. Yeah, and so because so this is so I understand the point Tanner's making is this step, because your COs are even stronger pi acceptors than acyl metals. This intermediate becomes more stable if you have a phosphine as your other ligand. I think that's what I meant. Okay, so we just have a couple minutes left. I think I can get you out of here on time for a change. And so I'm just, in closing, going to introduce two families of reactions that are related. So hydroformylation has been integrated as a key step in many different cascade processes. And one that's important industrially is the so-called hydroaminomethylation, actually a very old reaction. And so in this case, you can have a single catalyst, or if you're feeling more adventurous, a dual catalytic system that allows you to accomplish first hydroformylation, and then if you see a secondary amine and an aldehyde in solution, then you'd immediately be thinking that's going to form the corresponding iminium, and then ultimately the enamine, and then you can take advantage of the hydrogenation reactivity of these types of catalysts to then produce. And this is actually an old reaction developed at BASF by a familiar name, Walter Reppe, whose name who we have learned about in the cycloaddition class. And then another class of reactions I think hopefully this serves at least somewhat of a nice segue to the first class of the second part of this course, which we'll do after the exam, because many of these reactions are palladium catalyzed. The first class, after we meet again after your midterm, will be on Heck and Fokker chemistry. And these are hydrocarboxylations. So you can think of these as being analogous to hydroformylation, where instead of coming in with a hydride in that last step, now we're able to intercept with different nucleophiles. Here I'm just showing oxygen-based nucleophiles, but you can also do this with nitrogen-based nucleophiles. Typically, the reaction is linear selective with aromatic alkenes, then the selectivity is flipped. And I'll just show a general catalytic cycle here to round out the class. So let's consider the case of an alkyl substituted. Then migratory insertion is going to happen to give the terminal alkyl metal. I'll draw the H atom so it's clear what happened in that step. Coordinate a CO molecule. Migratory insertion to make a palladium acyl. And then we showed previously how to think about this step in either an inner sphere or outer sphere type pathway. I will draw it as being undefined in this case. and then the hydrogen atom from your incoming nucleophile ultimately regenerates your plate layer. Or perhaps more precisely, because the reactions are often added and often run in the presence of acid co-catalyst. After this step, you can get down to palladium 0, which then can react with the acid to make a palladium 2 hydride. And I think one of the key things I'll just say in closing is that if there's in the past, say, 15 years, there's been a significant amount of work done in the area of hydrofunctionalization, both hydroamination and hydrooxygenation methods. And I think one of the things that, particularly if you're honest with yourself, you have to think about is there are often other types of connections you can use to get to the same types of products, particularly when you're dealing with simple alpha olefins. So, this you could recognize as the same product that you'd get out of anti-Markovnikov hydroamination of an N+1 terminal alkene. And similarly, you can do sequences like hydrocyanation and then reduction to get to these types. So there are lots of different entryways to get to terminally functionalized products, and I think it's important to contextualize new methods in light of these sort of sequential approaches that you can do on massive scale really efficiently. Okay, that's all. As a reminder, there's a review session. Joe, do you want to say?
Yeah, sure. It's at 3. It'll be at Tech.
3 at Tech. No class on Monday, and then the exam on Wednesday. Normal class time. 2 hours, 45 minutes.
Yeah, we can pick that up.